Hello, you're welcome back. Okay, so now we looked at previously current electricity. Okay, and we actually talked about electric current flowing through a conductor, and of course we talked about electromotive force. Okay, delivering potential difference to an external circuit, and we actually drew a circuit diagram that shows how electric cell delivers current to an external circuit. So we're going to be looking at DC circuit. Okay, so in this tutorial we're going to be looking at a whole lot of circuit diagrams. All right, okay, now circuit diagrams that actually deals with passive component. Okay, all right, before then, our objective, don't forget our objective, okay, is to actually look at basic terms and definitions, state principle if it is necessary, okay, state formula and derive formula when it is necessary, okay, then of course solve questions. Okay, so that is the whole. And then of course we're gonna be using a guideline questions. Okay, there's gonna be questions, we'll pick questions. Okay, and of course as we actually solve the question, I'm going to explain uh, different terms, phenomenons, and of course formula. Right, so let's actually begin. So now we are looking at DC circuit. Okay, first of all, what is DC? This is direct current. Okay, now a direct current is a current that flows in one direction, and mostly, okay, what actually provides direct current is a cell, an electric cell, electrochemical cell, like a battery. A battery, okay, provide direct current. Okay, so whenever a battery delivers current, it's always moving in direction. It doesn't change direction, it moves, okay, directionally, returns back. From the positive it goes around and return back. Okay, now DC current is different from alternating current. Alternating current is that, okay, in alternating current, please pardon me, in alternating current, okay, the current actually varies with time. The current is not steady, okay, and it doesn't flow in one direction, right? It changes and of course varies, it fluctuates. All right, so now we're going to look at circuit known as DC circuit. Now a DC circuit, okay, is mostly made up of, okay, some um, passive component, okay, but the component we are going to be looking at, okay, here is a component known as a resistor. Right, now passive component is not just resistor, right? We have a passive component, is a component that does not only allow current to pass through it, it doesn't change the current, it doesn't magnify the current. Okay, it's either it suppresses the current, okay, or allow the current to just pass through it that way. But there are some component known as active component that takes little current, okay, and of course magnifies it. Okay, but that is just by the way. Now what we are looking at here is definitely a circuit that is made up of what? Resistor. Okay, now what is a resistor? A resistor is a device, okay, that actually that is used to oppose the flow of current. Remember, we talked about resistance. We said that resistance is the opposition to the flow of current. Okay, so devices that are manufactured, okay, to oppose current is known as resistor, right? So if you go to electrical shop or workshop, okay, you're gonna be given some devices, and you'll be told that they are resistors. Okay, what they do is that they are used to oppose current, and of course a resistor, okay, is being measured as in its resistance. Every resistor has resistance, all right, and of course the resistance is measured in ohm. All right, so now the symbol we're going to be using for resistor in a circuit diagram is this. Okay, so we use this symbol, we're gonna use this, or we use this. Okay, this one is more easier for me, right? So this symbol represents, okay, electrical symbol of a resistor, right? So now let's actually proceed with the question. Remember, we work with questions, right? Okay, so I'm gonna take the very first question. then we do justice to it. Okay, here we go. All right, now the question goes like this: derive the expression for the equivalent resistance of three resistors connected in series. Okay, connected in series. So that is when we want to derive expression for equivalent. The equivalent resistance is something as the total resistance when you have three resistors connected in series. So I'm going to draw the circuit diagram of series connection. Okay, this is what I'm going to do. Okay, so I will use, let me use this simple diagram for resistor, right? Or better still, let me use this. Okay, I think I should use that, right? Okay, so I'll copy it. So there are three of it, so I'm gonna, and they're connected in series, so I'm gonna put three in series. Right, one, of course two, right, three. Okay, so this R1, this R2, and of course this R3. Don't forget that I need to provide EMF voltage, okay, so I'm not considering internal resistors now. I'm looking at a cell without internal resistance, okay. So once you connect, this is called series connection, okay. Once you connect the cell, the resistors in series like this, what happens? Current flows, okay. The current flows, enters the resistor, the same current goes through this resistor, so the same current passes through all of them, okay. So for series connection, okay, this, which number is this now? Okay, number 2. So for series connection, please take note, current is the same. The current is the same, but what actually varies is the voltage, okay. The voltage across this is different, but for current is the same, okay. So voltage, or the PD, varies. So with PD varies, that means the PD across R1, I call it V1. The PD across R2, I call it V2. And of course, the PD across R3, I call it V3. Alright, so that means the total PD now is going to be the combination of V1, V2, and V3. So the total PD that is delivers, okay, V total is going to be the PD across V1 plus PD across V2 plus the PD across V3. Remember Ohm's law. According to Ohm's law, V is equal to IR. Okay, I hope you can still remember this. And don't forget that the current is the same. Current across all of them is the same. Okay, so I will still remain. Okay, so now I have to substitute. So for V total, I'm gonna have V. Sorry, please pardon me. Right, for V total, I'm gonna have I all over R total. Okay, so which definitely is equal to, gonna give me I multiplied by R1, then plus, remember the I is the same, okay, I is the same, I for V2, I multiplied by R2, then for V3, okay, I multiplied by R3, okay, because V is IR and I is the same, okay, that's why CI the same, or true, I is the same for series connection, okay. So now what do we do? Alright, since I is common, okay, I'll factorize it out. I'll take it out as a factor, then I'll write the other factor inside, the other factors inside, which is R1 plus R2 plus R3. Alright, so now having two factors, okay, I found both sides of the equation, so they actually cancels out. All right, they cancel out when you have these two factors. All right, when you have the same factor, okay, find both sides of the equation. Okay, I is find both sides of the equation. They will cancel out. Okay, at the same point, that is numerator. Please take note of that. All right, this is mathematics. All right, so I'm now left with the total resistance, okay, for series connection is going to be equal to R1 plus R2 then plus R3. So please take note, when resistors are being connected in series, to get their total resistance you add them R1 plus R2 plus R3. So this is the derivation for series connection. This is series. Remember, we're asked to derive both series and parallel. Okay, so now let's look at parallel connection. All right. All right. Let's look at how parallel connection works. So I'm gonna draw for parallel connection. Okay. I'm gonna draw for parallel connection. This is how it looks like. Okay, so I will. Okay, this time around, let me still use the normal resist. Or better still. Okay, let me use this type of resistor. Okay. Okay. Okay, so I'm using this type this time around. Okay, so here we go. So I press. Okay, take another one. Then take another one. Okay, so this is parallel connection. Okay, and of course I connect it across all of it across potential difference. All right, so let's say this is R1, this is R2, and of course this is R3. All right, so now let's see what happens. Okay, current flows when I supply the voltage enters into the parallel. Okay, because anytime there's a parallel, that's one thing you normally used to know. Where there's parallel, there's always going to be a branch. Current will divide. That's what makes parallel. What makes parallel is just, it's not necessarily, doesn't necessarily mean that the two resistors are facing each other. It's just that at the point where there's parallel connection, there's always a branch. Okay, current divides. Current enters into R2. Some current enter into R2. Some current enter into R3, R2, and of course R1. So this current I will definitely divide. Okay, the current divide. Okay, so which simply means that, but the voltage across R1 and R2, since they are connected in parallel, okay, is the same. So in parallel connection, please take note, V is the same. All right, but what actually varies is I varies. Now since I varies, okay, that simply means that the total I that enters into this is being divided into 3. Okay, the I that's entering into R1, I call it I1. The I that's entering into R2, I call it I2. And the I that's entering into R3, I call it I3. Okay, so that simply means that I total is going to be equal to I1 plus I2 then plus I3. All right, so let's go there. According to Ohm's law, we know that V is equal to IR, okay? So making I the subject of formula, we know that I is going to be equal to V all over R. So putting that in this relationship, so I have that for I total, okay? That's going to be V. Remember, V is the same, so that's going to be V all over R total, right? Now for I1, the same V, which is this all over R1. For I2, V all over R2. Then for I3, V all over R3. Oh, okay, so of course, knowing that V is common and is the same, I can always factorize it. I'll take it out as a factor, right? Open a bracket, then I have 1 all over R1 plus, right, 1 all over, because V is already outside, okay? So this now, what I have left at the numerator is 1 all over R2, then 1 all over R3. Alright, of course, you know what happened? V is found in the same position numerator, both sides of the equation, they will cancel out. So that you are left with 1 all over RT, okay, is equal to 1 all over R1 plus 1 all over R2, then plus 1 all over R3. Okay, so please take note of this. So for parallel connection, okay, the reciprocal is always in the reciprocal. The reciprocal of the total resistance or the equivalent resistance is equal to the sum of the reciprocal of the individual resistance, okay? It's always in reciprocal, but for series, it's just a sum, okay? So please take note. We did this when we did take a capacitor. Remember, capacitor is opposite, okay? Opposite of resistor in terms of equivalent. For capacitor, okay, the series is always in reciprocal form, while the parallel is, okay, the parallel is in a sum form, okay? So just know the difference, okay? I think we've done justice to that question there. Okay, so I think we can actually look at the next question. The next question, okay, is, let's see, the next question is an example, okay? And I love examples so that we can illustrate this, okay? So it's an example of what we did. So the question is, evaluate the resistance of the equivalent resistance of the circuit below, hence determine the current I, okay? So circuit A and circuit B. All right, so this is circuit A. So now let's analyze the circuit. All right, if we analyze the circuit, it's called that 6 ohm, excuse me, I'm starting with A, 6 ohm and 3 ohm. This is already parallel connection, okay? Now when I resolve this parallel connection will become one resistor which is connected in series with 4 ohm, okay? So first of all, I'm doing a part. So let me resolve the parallel connection. Let me call it now, of course, since there are two, remember in parallel connection we have that 1 all over RT. Okay, let me use P, parallel, okay? It's going to be equal to 1 all over R1. That's 1 all over 6 plus 1 over 3. 1 all over 6 plus 1 over 3. Now remember, I gave you a shortcut of when you have two resistors connected in parallel, to just, instead of going through the LOCM process, you can just do product all over sum, okay? Product all over sum. What is the product of the product of the resistor is 6 times 3 divided by the sum of the resistors, 6 plus 1. But if you like, you can go through the LCM, okay? You just use what is convenient for you. So 6 times 3, that's what? 6 times 3, is that 18? Okay, that's 18, right? So I'm gonna have 18 then divided by 6 plus 3, excuse me, 6 plus 3 is 9, okay? So I have 18 divided by 9, okay, which is 2 ohm, okay, 2 ohm, 2 ohm. Okay, so now this is 2 ohm being the whole of this. So that means 6 ohm and 3 ohm. After resolving it, it gives me 2 ohm. So I can actually just use one resistor to represent it. Then if you look at it, if I redraw this circuit now, okay, 2 ohm now, okay, this, the whole of the 6 and 3 is 2 ohm, is connected to 4 ohm in series. It's connected to 4 ohm in series. Okay, so now the total resistance, now remember series connection, RT is going to be equal to 4 plus 2, which is 6 ohm. All right, 6 ohm. That is the 4A part. Now remember the question is evaluate the equivalent resistance, okay, and of course the current. So how do we evaluate the current? Remember from Ohm's law, V is equal to IR. All right, so I have I being equal to V all over R, okay? So what's the V? The voltage is 18. That's 18 divided by 6, which of course is, that should be 3 ampere. So that's the current. Okay, so the B and the C part, okay, it's very easy. I'll give you the opportunity to do this, okay, as a kind of class work. Then of course I will do it in the next video. So just go through this and we'll see in the next video. Thank you. Hello, you're welcome back. Okay, so now we looked at previously current electricity, okay, and we actually, you're welcome back. Okay, so now we're going to continue from where we stop. All right, so previously we looked at resistor circuits, okay, resistors in parallel and the resistor in series. Okay, so now remember this topic is DC circuit, so we're going to be looking at different form of DC circuit. But before then, let's look at Kirchhoff rules. Okay, now why do we apply Kirchhoff rules? Okay, now there are some circuit, some network, okay, that you can actually reduce to series parallel like we did before, okay, where we actually reduce a circuit, okay, we differentiate a series and a parallel connection of resistors, okay. Now there's some circuit you cannot actually differentiate or reduce it to a series parallel connection. So such case, okay, you apply Kirchhoff rule, okay. So now what are Kirchhoff rules? So now Kirchhoff actually states 2 rules. One of the rules is known as loop rule, Kirchhoff loop rule, or you call it voltage, okay, Kirchhoff loop or voltage rule. So what does it state? Okay, now Kirchhoff loop or voltage rule state that the algebraic sum of voltage around a loop is equal to 0. The algebraic sum of voltage around a loop, okay, so that's the sum of all the voltage around a loop is equal to 0. Now the question is, what is a loop? A loop is simply a closed path that current actually travels, okay. For example, this is a loop. If I should draw this, a resistor connected to, okay, a resistor connected to a battery, okay, this is a loop because current goes like this, returns back, okay. So you say that the total voltage, if I should sum all the voltage in a loop, let's say this voltage is V1, okay, and this voltage is V2. If I should sum it, okay, with their sign, it will always is equal to 0. So that is a Kirchhoff voltage or loop rule, okay. So now secondly, Kirchhoff also states another rule known as the junction rule, okay. Kirchhoff junction rule, junction or current, Okay. All right. So instead that the algebraic sum of the current entering into a junction is equal to the algebraic sum of the current leaving the junction. All right. Let's say we have a junction. Okay. Junction is a point where there's a branch. That point where they have a branch. Okay. Let's say this is a wire. Okay. Of course, let's say current is entering this and it reaches here. Let's say this is a junction A. Okay. Now it branches, one enters this, one enters this. Okay, so this current is entering, and this current, let's call this I1 is entering the junction A, then I2 is leaving the junction A, I3 is leaving junction A. So according to him, he said that the total current I1, the one that is entering junction A, is equal to the sum of the current that is leaving junction A, I2 plus I3. Okay, so please take note of that. All right, so we are going to be looking at question, okay, that applies Kirchhoff rule. So that's what we're going to do now. Okay, I'll just get a question. Okay, here we go. Excuse me. All right, so this is the question. It goes like this: find the current in every branch of the two-loop circuit shown in the figure. Okay, so as you can see, this is actually two loop. Okay, here we have loop 1 and here we have loop 2. So now there's a junction here at A. As you can see here, there's a current I1. This current here is I1. All right, and this current is entering, and of course the arrow is shown. Okay, then of course current I2 is also entering A, is moving towards A, but this current the current that's leaving towards A is this current here, and of course according to Kirchhoff, okay, the current that's entering is equal to the current that's leaving. So this current that is leaving this junction A is going to be the sum of I1 and I2, I1 plus I2. So please take note. So the question is, we are asked to calculate all the current entering the in the order branch. Okay, so the current in order branch is I1, the one that's entering into, that's in this branch. Okay, then of course I2, the one that's branching here, then the sum. So now that simply means that we are looking for I1 and I2. They are two unknown. So if we're looking for these two current I1 and I2, that means we need two equations, because we need to solve a simultaneous equation for you to find two unknown. All right, so how do we actually generate that equation? We apply Kirchhoff voltage rule. Okay, so remember voltage rule, the voltage, sum of the voltage around a loop is always equal to 0. So now that means you have to add up all the voltages. Now if you're adding voltages in a loop, okay, like this is loop 1 and this is loop 2, right? Now if you're adding voltage in a particular loop, there's something you should take note of. Okay, all the resistors that's connected to the negative part of the source, like now this is resistor 2 ohm, this side of it is connected to negative, so this side of the resistor has its negative sign, while the other side is positive. For this resistor 8 ohm, this side is connected to positive, right? And of course this side is connected to negative. Now if I should go the same way, okay, if I should trace it to this resistor 5 ohm, I'm looking at the first loop here. Okay, this first loop, resistor 5 ohm, if I trace it, this side is negative for 5 ohm and this side is positive. All right, so now I can add the voltage. Now if you're adding voltage, okay, applying Kirchhoff loop rule, that's one thing you should know. Anytime you're going around loop, you're actually moving, whether you're moving clockwise in the clockwise direction, anti-clockwise. If you encounter positive first, okay, then definitely that voltage will be positive. But if you encounter negative first, the voltage will be negative. All right, okay, let's say I'm starting from the battery. Okay, let me start from the battery, move from the positive. Okay, so moving from the positive, I want to go clockwise. All right, so if I move from the positive like this, right, in the clockwise, I count the 8 ohm. All right, is positive. I encounter positive first, so this simply means that the voltage is going to be, remember, voltage of according to Ohm's law, voltage is always equal to IR, right? Okay, so if that being the case, what am I going to do? So I'm going to multiply. What's the current? The current that's passing through 8 ohm is I1. Remember, I1 is the current that's going through the first loop. Okay, so that's going to be I1, then multiply by 8. All right, so let me still be moving. I move, then I encounter 5 ohm, positive part of I5 ohm, right? So the current that's passing through 5 ohm is I2. So that's going to be I2 multiplied by 5. Okay, I still move in a clockwise direction, go. Then I encounter 2 ohm. Current passing through 2 ohm is I1. Okay, I1 is the current passing through the first loop, all right? Because this I1 is moving from through the loop, all right? So I1 is the current passing through the 2 ohm, okay? And of course it's plus. Then I now encounter the source, voltage source, okay? I encounter the negative part of the voltage source, so that's going to give me minus 120. Now, according to Kirchhoff, the whole of this, if I add the whole of these voltages, it should give me 0. So I'm done with loop 1, but let me evaluate that first. Okay, so this is going to be 8I1, right? Then plus, I'm adding items now, 2I1. 8I1 plus 2I1 is going to give me 10I1, right? Then of course plus 5I2, right? Now equal to, I'll take the minus 120 to the other side because plus 120, this is my equation 1 for loop 1, okay? So let's go to loop 2. I do the same thing to loop 2, okay? I move in a clockwise direction and start with the source, okay? So starting from the source, okay? So the source now, that will be plus 14, right? Then I now move. If I go to the next resistor, that's going to be minus, okay? Minus, that's 1 ohm. Remember, the current passing through the loop 1 is I1 plus I2. So that's going to give me 1 multiplied by the current, okay? Or better still, the current multiplied by the resistor, still the same thing, okay? Close the bracket, go. So remember this negative, if I still trace it, so this 5 on here is still, I'm countering negative, right? So that's still gonna be minus 5I2. Alright, so let's rearrange this equation. So this is gonna give me 14, right? Then if I open this bracket, minus 1 multiplied by I, that will give me minus I1, right? Then of course I have minus I1, and of course if I multiply this, I have, okay, that's gonna be minus I2. Minus I2 minus 5I2 will give me minus 1I2 minus 5I2 will give me minus 6I2. Okay, let me see if I open this bracket and of course collect items, that's going to be 6I2. Then of course is equal to 0. So I'm going to rearrange this equation. I carry all this to the other side of the equation, okay? So if I carry minus I1 to the other side, it becomes plus I1 minus 6I2 will give me plus 6I2. Alright, then the 14 remain at the other side where it is, okay? Alright, so this is equation 2. So I'm solving this equation now. Equation 1, equation 2 simultaneously. So I will use substitution method. So what I will do, I will now substitute. I will say from equation 1, okay, I1 is equal to, I'll make I1 the subject, okay? That's going to be 14, right? Minus 6I2. 14 minus 6I2. So I can now substitute. Since I've gotten it from equation 2, I'll substitute I will sub it into equation 1, right? So that's going to be substitute, right? I2, I1, okay, being equal to 14 minus 6I2, right? Into equation 1. So if I go to equation 1, any place I see I1, I put 14 minus 6I2. So this is my equation 1. That's going to be 10 into open bracket, okay? 14 minus 6I2. Okay, close, then plus 5I2, right? Okay, it's going to be equal to 120. All right, so let's work on this. So this is going to give me 10 multiplied by 14, that's going to be 140. Then minus 60I2. Okay, plus 5I2 is equal to 120. All right, 120. Okay, so now subtracting this, I'm gonna have, okay, minus 60I2 plus 5I2 will give me minus 55I2, right? Okay, and of course, if I take this to the other side, that's gonna be 120 minus 140. I think this gives me 60. That gives me 20, right? Okay, hope I'm not mistaken. That gives me 20. So I have now I2 now is going to be equal to 20. That gives me minus 20. Please pardon me, okay? Of course, minus cos minus. So my I2 now is going to be equal to 20 divided by 55. Okay, let's use calculator. All right, so that's going to give me 20 divided by 55. So 0.4 approximately. 0.44 ampere. Okay, so for me to get I1 now, I have to put I2 into this equation. So I1 now is going to be equal to 14 minus 6 times 0.4. 0.4, right? So that's going to give me 14 minus 2.4, right? Right, so this is going to be equal to, that should be 12, okay? 14 minus, excuse me, 14 minus 2.4 gives me 11.6 ampere. Alright, so please take note of that. That's Kirchhoff law. Okay, as we proceed, let's look at the next question. Okay, now I bring it to this screen. Okay, so this one goes this way. Based on construction, what is the difference between voltmeter and ammeter? All right, what is the difference? Now, of course, you know that a voltmeter force, okay, which of course this is a symbol of a voltmeter, okay, is a device, it's a measuring instrument for voltage. It's an electrical measuring instrument for voltage. Then of course ammeter. Okay. Is used for current. Alright, so this one measures voltage, this one measures current, but we ask based on their construction, how are they constructed? Alright, now both voltmeter and ammeter is being constructed from another instrument known as galvanometer. Now what a galvanometer does is, okay, actually it is a coil, okay, that has a magnetic field inside of it that deflects. Okay, remember, anytime there is electricity or current inside magnetic field, there's always going to be a motion, there's going to be a torque. So galvanometer only detects, okay, as current actually enters into it. All right, it causes the pointer to deflect based on the current. But one thing about a galvanometer is that it can only measure small amount of current. So we call it micro ammeter. Okay, this is an ammeter, right? But a galvanometer is called micro ammeter because it only measures micro amount of current, very small amount of current. Okay, but a galvanometer or a microammeter, okay, can actually be converted to a voltmeter, okay, and an ammeter, and that is exactly the construction now. Okay, now for you to actually convert excuse me, okay, so you are starting with converting a micro ammeter or galvanometer, okay, macro ammeter into an ammeter. All right, now for you to actually do this converting a microammeter only measures very small amount of current, micro current, but an ammeter measures normal current, okay, up to ampere, but microammeter measures current in as small as micro ammeter. Right, so please take note of that. So for me to actually do that conversion, look at what's going to happen. Let's say I use G to represent the microammeter. So I want to apply a current I that a galvanometer will measure. Okay, now because a microammeter can only measure, okay, small amount of current, let me use IG. Call this IG full scale deflection. That's the maximum current it can measure. Okay, so that simply means that if I apply this current to it, it will damage it. So all I just need to do, I need to divert it. So I need to divert it. So all I do is I have to connect a resistor to divert some of the current, and that resistor is known as shunt resistor. Okay, so if you are being asked how do you convert a microammeter to an ammeter, okay, you convert a microammeter to an ammeter by connecting a shunt resistor in parallel. Please, this parallel connection with the galvanometer, so that as the current actually enters into this branch, okay, galvanometer can only take its maximum current, which is known as IG. Then the excess current, now remember the excess now is going to be equal to I minus IG, okay? So the excess current, which is I minus IG, is what will enter into the shunt, okay? So the whole idea is you'll be asked what is this resistor, okay, that will be able to take this excess current. What is this shunt resistor? What is the value? All right, to get the value of the shunt resistor, we can actually get that. Remember, both the galvanometer and the shunt resistor, they are in parallel. And you are told that when components are in parallel, their voltage is the same, okay? So I can simply say that, okay, the voltage of the galvanometer, VG, okay, is equal to the voltage of the shunt resistor. All right, and of course, according to Ohm's law, voltage is equal to IR, okay? Now, let's say that this galvanometer has internal resistance of Rg, all right? So I can now simply say that, okay, the voltage of the galvanometer is Ig Rg, okay, it's equal to the voltage of the shunt. The current of the shunt is I minus Ig. okay, I minus Ig. All right, then multiply by Rx. So for me to now look at what I'm looking for, this Rs. So the shunt resistor that is needed, okay, to convert a microammeter to an ammeter is given as Ig Rg divided by I minus Ig. So please take note of this, okay. Now where Ig, as you see here, okay, is actually known as the maximum current or the full scale. It's being called the full scale deflection. Full scale deflection. So the only current that will give a galvanometer is full scale deflection. All right. Of course, the I is the current that you want to measure. Okay, the current you want to convert. The ROG, of course, is the resistance. Resistance of the galvanometer. And of course, what again? Okay, Rx is the shunt resistance. All right, so please take note of that. So take note of this formula. That's how we can construct an ammeter, right, from a galvanometer or microammeter. So I'll clean up. Let's look at how we can actually construct a voltmeter. Okay, so let's say we have galvanometer, right? Galvanometer G. Then I want it to measure a voltage. I want it to measure a voltage V of voltmeter. So if I should actually apply the entire voltage of voltmeter, okay, it will damage it. So what happened? I need to split the voltage. So for me to split the voltage, I will definitely have to connect a resistor, okay, in series. And this time around, the resistor I have to connect in series, okay. We call it multiplier, Rm, okay. So please take note. And of course, this is Rg. If you want to convert a voltmeter to a galvanometer or microammeter to a voltmeter, you need to connect, okay, you need to connect a multiplier, all right, a series with it. This is series. Remember, short it was parallel, okay. So what is the whole idea? Now remember, the galvanometer still need to take only the maximum current, which is Ig. And since these two, both the multiplier and the galvanometer is connected in series, the same current that galvanometer will take is what is passing through this, okay. So that means the same current Ig that's passing through galvanometer is what will also pass through. Now what happens is this voltage from the voltmeter will be divided, okay. Some will definitely go to the galvanometer. Let me call it Vg. Then of course the shunt will take its own voltage, the multiplier rather, okay, that's its own voltage. So that means the total voltage that should be measured by the galvanometer, the total voltage, okay, of the voltmeter, okay, is gonna be the sum of the voltage of the galvanometer Vj plus the voltage of the multiplier Vm. Okay, applying Ohm's law, okay, Vj is gonna be Ig, okay, full scale deflection of the galvanometer, then multiplied by Rg, okay. Of course, Vm is taking the same current Ig, okay, but multiplied by the Rm. So remember, the whole idea of this is for me to get this resistor, okay, the multiplier resistor, okay. So this is plus this. All right, so I have to rearrange this equation. You know what I do now? I take this to the other side. So I have that Ig Rm is going to be equal to V minus Ig Rg. So at Rm now, the multiplier resistor that is actually needed to achieve this is going to be equal to V minus Ig Rg, alright, then divided by Ig. Okay, so V is the voltage of the voltmeter, right? The voltmeter voltage, or the voltage you want to measure. Okay, Ig is the full scale deflection of the galvanometer. Rg is the resistance of the galvanometer, and Ig is the full scale. Alright, so that is it. So write it down, write the formula down, of course. Always know how to apply it. Okay, so let's proceed to the next question, if we do have one. Okay. Okay, so all right, now before we actually look at question, now let's look at more circuit. Remember, this we are talking about DC circuit. Okay, so let's look at more circuit that you ought to know. Okay, now I'm going to mention only two. So one of the circuits you need to know about is a circuit known as meter bridge circuit. Now a meter bridge circuit is actually a circuit that has a length of a wire connecting two resistors, okay, in which one of the resistors is an unknown resistor, the other one is a known resistor. So I can use a meter bridge to find an unknown resistor. Okay, now let me just give you a typical example. Let's say I've got two resistors, right? These two resistors. Then I'll connect two of it, okay? I'll connect this to a length of a wire. This is a length of a wire, okay, known as meter bridge. Okay, in between I now connect two of the resistors. Then I'm going to use a galvanometer with a jockey to touch this length of a wire. Let's say the length of this wire is 100 cm. Let's say from here to here to the end of the wire, okay, is 100 cm. Now don't forget that I'll have to supply voltage to the network, okay? I have to supply voltage to the network. So let's say this is a resistor that is known. Let me use X to represent the resistor that is not known, okay? Let me use Rx to represent the resistor that's not known. Alright, so if that's be the case, okay? So now I will be using this galvanometer as I set up the connection. I use this galvanometer to be touching each point of this wire, this 100 cm of a wire. Okay, it's a type of wire, it's a resistant wire known as constant wire. And what am I looking at? I'm looking at the point where the galvanometer reaches 0. Okay, at the point where the galvanometer reaches 0, I will say that's a balance. Okay, which simply means that the left hand side, the right hand side is in balance with the left hand side. Okay, that's why the galvanometer is reading 0. That's why the potential between this and this is 0. Okay, so at that point I'm going to write a formula that will relate R and Rs. So here is the formula. So please take note, assuming the balance is actually, let me say the balance from here to here, the distance is X. Okay, that means what is left from here to here is going to be 100 minus X. Okay, 100 minus X. -100 - X. All right, so now with what is going on here, we have a ratio. I'm going to create a ratio. We have R divided by Rx. We have R divided by Rx, which is going to be equal to okay, R divided by Rx. Now the R is balanced at X, okay, going to be equal to the ratio of that balance, X divided by 100 minus X. So that is the ratio relationship we normally use to evaluate meter bridge. Okay, I will do more in the next video. Thank you. You're welcome back. Okay, so now we're going to continue from where we stop. All right, previously we looked at resistor circuits, okay, resistors in parallel and the resistor in series. Okay, so now remember this topic is DC circuit, so we're going to be looking at different form of DC circuit, but before then, well, let's look at Kirchhoff rules. Okay, now why do we apply Kirchhoff rules? Okay, now there are some circuit, some network, okay, that you can actually reduce to series parallel like we did before, okay, where we actually reduce a circuit, okay, we differentiate a series and a parallel connection of resistors. Okay, now there's some circuit you cannot actually differentiate or reduce it to a series parallel connection, so such case, okay, you apply Kirchhoff rule. Okay, so now what are Kirchhoff rules? So now Kirchhoff actually states two rules. One of the rules is known as loop rule, Kirchhoff loop rule, or you call it voltage. Okay, Kirchhoff loop or voltage rule. So what does it state? Okay, now Kirchhoff loop or voltage rule state that the algebraic sum of voltage around a loop is equal to 0. The algebraic sum of voltage around a loop. Okay, so that's the sum of all the voltage around a loop is equal to 0. Now the question is, what is a loop? A loop is simply a closed path that current actually travels. Okay, for example, this is a loop.